Okay, so we've been talking about polar coordinates, cylindrical coordinates, spherical coordinate stuff for most of today. So reminder, the big idea here is that those coordinate systems conversion formulas can be repurposed as change of variables functions. And we've done examples of all of those. The next big idea was, even though we're using them as change of variables functions, we're pulling back the domains. We don't really have to draw that. Everything we need to see about those new domains is visible in our existing pictures. Right? So we did that with polar, we did that cylindrical, now we're going to do it with spherical. Here's what cross sections look like in spherical coordinates. This here is what a constant fixed value of rho looks like. That's a very strange kind of a slice to take. I don't know of any knives that do that. Right? Here is a fixed value of phi. Right? Keep in mind phi is angle off of the z-axis, positive part of the z-axis. So you could probably do that with a knife, but it'd be a tricky cut. And then here's what a constant value of theta looks like. So these are our various different slicing options. Just due to the geometric complexity, I think is a very strong argument that this should always be first. Right? Don't try to take spherical cuts. Not that you can't, but it's harder, and why would you want to make your life harder? Right? Okay. Now, inside of those kinds of cuts, let's ask, what does a rho slice look like inside of that theta slice? Well, it's, round. Right? What does a phi slice look like inside of a theta slice? Well, it's a straight line. So, which of these is easier to deal with? Well, that one is easier to deal with. Right? So, this is what I encourage. Always do your theta slicing first, then do your phi slicing second, and then the rho slicing, well, that's just observing, what's the range of values then of rho on your phi slice of your theta slice. That's sort of the geometrically easiest choice. And this is another one of those situations where vast majority of the cases that you're going to be looking at, such an overwhelming majority that I can't think of any examples where this isn't true. D rho, d phi, d theta is always the right choice. So always do it in that order. Okay. Alrighty. So let's consider this case. We're going to go in detail through this example. So we have here a ball of radius A centered not at the origin, but at 0, 0A on the x-axis. So this is a ball that, where did my picture go? Here it is. It's a ball that's kind of sitting on top of the origin. Sitting on the xy plane at the origin of radius A. Okay, suppose that's our domain. Quick reminder, if this were our domain and if we were doing rectangular coordinates, it'd be a nightmare of square roots. I don't want to do that. Okay, so real quick, let's go ahead and take this ball and let's find its spherical equation. There's the rectangular equation. Notice the center being at 0, 0A is why we have that minus A there. The radius being A is why that's there. Right? There's the equation for that sphere. And we convert into spherical coordinates by, this is a chapter 1 thing? Was it chapter 1 or chapter 2? I forgot where I put that. I think it was chapter 1. But anyway, by old methods, it's just a matter of plugging in the conversion formulas that we already know. You can see that x squared plus y squared plus z squared is going to happen. That's rho squared. And then we have other formulas. For this z here, we have an existing formula for what z is in terms of rho, phi, and theta. Plug it in, work it out. There it is. So let's keep that in mind as we go along. Okay. All right. So this shape, let's think about our theta slicing. Here's what theta slices look like, as previously discussed. A theta slice is a plane, it's a vertical plane hinged on the z-axis. Represents a constant value of theta. And now, again, you could try to do the pullback and figure out what that pullback domain looks like much easier. Let's just ask, what's the range of values of theta that sweeps out this entire solid? Well, 0 to pi. This solid envelops part of the z-axis, and so you're going to have to go all the way around to get all of it. So theta goes from 0 to 2 pi. You can see it right there in the picture. I don't need the pullback. Okay. All right. Now, these pictures get ugly fast. So I have a suggestion, and it's not always the case that this is the right thing to do, but it is often the case. So I want to encourage y'all to do this unless there's just a really good reason not to, or if the geometry is really simple and you just not a problem, you don't have to. But here's the suggestion. We've got this theta slice, right? You can draw what the actual theta slice itself looks like. The actual theta slice. Oh, come on. Let's do better than that. The actual theta slice is this. Draw that theta slice by itself, head on. Like, in other words, ignore the fact that this is sitting in R3. Just imagine that this is like a piece of paper that's standing there. Pick up that piece of paper and set it down flat on your desk, right? So looking at it straight on is just easier. So here it is. Here's, our theta slice, constant value of theta, right? The actual cross section was that. And it's just going to be easier to see what phi is doing. It's going to be easier to sort of understand this picture as opposed to that picture. This picture, we're looking at kind of a stance. We're kind of sideways looking at it. We're kind of above. And it's just weird and hard to see what's going on down here at this corner that's going to end up being important. Right? And I just think it's easier here. For one thing, it's two-dimensional picture on two-dimensional paper. That's already a good thing. Does everybody understand the suggestion here? Okay. Now, by the way, one thing to keep in mind, this is a little sloppy, but feel free to do the following. I can kind of think of this as sort of being, kind of an R-axis. It's not really, right? But it makes you feel a little better to think of it that way. And then likewise, this is the Z-axis, and it might be a little bit comforting to think in those terms. We have the R-axis and the Z-axis. Okay, so we've done our theta slicing. Next step, of course, is to think what's the range of values of phi. So looking at this theta slice, remember what phi is. Phi is the angle off of the z-axis as measured at the origin. So phi slices look like this. Right? You got to think, how far do you have to go until you get all of this disk? Half disk. And I appeal to your geometric intuition. The last slice is going to be where phi is pi over 2. The first slice, of course, was where phi was equal to 0. Right. Now this is a geometric appeal. So the idea is this half disk, right? We've got this half disk, and this half disk comes down here, and it's tangent to, again, loosely I'm going to call this the R-axis, the horizontal axis. Being tangent down there, if you take any value of phi that's higher, that where phi is a less than pi over 2, that's going to cut off, and therefore you'll be missing part of your disk. So 0, pi over 2. How do we feel about that? You guys happy? Okay. All right. So then we pick a value of phi. Now again, here we have our theta slice. Fixed value of theta. On that theta slice, we just agreed that on a range of values for phi. Here then is our phi slice. There's a phi slice of our theta slice. Last question then, what's the range of values of rho? Well, rho, it starts there. Oh yeah, question. Mm-hmm.
Would it have hurt us if we had chosen phi is equal to negative pi over 2 instead of 0?
Can't choose any negative values of phi, remember. Yeah, that's the little, yeah. So previous to this, your motivation to choose values of phi between 0 and pi was self-interest. It's just a little easier. It's geometrically more visible, right? So just, always make this sort of the natural choice. Now it's even more important. Now it's actually required. Yeah, totally. Okay, right. So on this phi slice of this theta slice, rho starts at 0, proceeds along to there. So again, it's pretty clear that this is rho equals 0 there. But at this point, what can I say about rho? And you have to just think it through. What do I know about rho at that point? Well, that point, don't forget, that point is just our sort of reimagining of a point like that. Right? And that point is on the sphere, and that sphere, we've already worked it out, has this equation, which of course in spherical coordinates is this equation. Right? So what I know about rho at that point is rho is already solved for. And it's 2a cosine phi. So let's write that down over here. Rho is 2a cosine phi. Of course, conveniently, we are already on a phi slice of our theta slice, so phi is fixed and known and given, and so I don't need to work out anything beyond this. This is what the ending value of rho is on that phi slice of that theta slice. Okay, so altogether then, theta goes from 0 to 2 pi. Phi goes from 0 to pi over 2, and then rho goes from 0 to 2a cosine phi. And we've got all that right here. Let's see that in the picture here. So theta goes from 0 to 2 pi. Phi goes from 0 to pi over 2. Rho goes from 0 to 2a cosine phi. That's all the stuff that we just worked out. Okay, let me zoom in for visibility. Don't forget, again, it's so easy to forget, don't forget your stretching factor. That is extremely important. Rho squared sine phi. Again, when you write it down, when you first decide you're going to use spherical coordinates and you choose to write down all the stuff at the end, write all this down all at the same time. Rho squared sine phi d rho d phi d theta, all at once. Always in that order. And then everything else kind of falls into your lap. The integrand, see the integrand that we were given was this. That's rho squared. So rho squared combined with this rho squared gives me rho to the fourth. And so, simplifying, then this is your final integral. And note, that integral's not that bad, right? Our alternative, our rectangular alternative would have been square roots everywhere, right? And here, instead, okay, there's a little bit of trig in that bound, right? But constant. We have a really nice set of bounds here, and the integral works out to be perfectly doable. Questions? Is everybody happy? Okay. Alrighty. So y'all have a bunch of examples that you're going to work out in the exercises here. I'll thin that out a little bit. But of course, you've got plenty to work on. If you want more after whatever I give you, then there's plenty of other ones to choose from. Okay, so we're going to move on now. We're going to talk about a new kind of integral. We've digressed from defining new kinds of integrals for the last couple of sections. We've been talking about how to compute integrals, right? But before that, we were defining new kinds of integrals. We had, single variable integrals was our old kind of integral. But then we defined something called a double integral. Brand new thing. It addresses what if you have a different kind of a domain, a two-dimensional kind of a domain, and you need there's some sort of accumulating quantity like mass or people or bacteria or what have you that's accumulating on that two-dimensional domain. Well, double integral is to chop it up, add it up, solution. What if there's an accumulation over a three-dimensional region? Well, we defined this brand new kind of integral called a triple integral. Here we're going to consider something a little bit different. To be more precise about the integrals we've just talked about, double integrals, it was a two-dimensional domain, but more importantly, it was a two-dimensional domain that lived in a two-dimensional world. We were looking at regions in the plane, right? When we were doing triple integrals, it was three-dimensional solids in a three-dimensional world. Three-dimensional solids in XYZ space. Okay. What if the dimension of the domain itself is not the same as the dimension of the world it lives in? And we're going to start off by considering a one-dimensional domain like a curve that does not live in a one-dimensional world. This is a one-dimensional domain that lives in free space. And look, this is a pretty natural question to want to consider. I mean, so maybe I have, our usual metal rod type of question. You know, what's the total mass of this rod if the density is not a constant? But where density was given as a function of a single variable x. What if density was a function of position in space, like this? Right? And I wanted to know the total amount of mass inside of this metal rod, or maybe this is a strange cave inside of a mountain, and there's stuff has accumulated, but it's accumulated more at the lower depths and less at the higher depths. Right? So it's still an accumulation. I'm still accumulating over a curve, but the integrand is a function of position in space. So this is a very different kind of a situation, right? A single variable integral, as we currently understand it, doesn't really address this. Everybody see what's new about this? So we've got to define a new kind of an integral. This is not going to be a Calc 1 Riemann sum. It's also not going to be a triple integral. Triple integrals talk about how things accumulate over volumes. Right? Importantly, this is to be thought of as a one-dimensional domain. Right? So it's just different. Okay. So big surprise. We're going to chop it up, add it up. So here's what that looks like. You chop it up into little pieces. You chop up this curve into little pieces of curve. Right? There's my first piece of curve. There's my second piece of curve, etc. You can talk about in different pieces of curve. This then is the ith piece of curve there. You chop it up into. This little picture is a little small, so we blow up larger just for visual purposes. That little piece of curve there, remember the chop it up, add it up strategy is that each new piece, I think of the piece as having a size. The quantity in question needs to be some integrand appropriate to the application. It gets multiplied by size. What is the size of a piece of curve? Well, it's the length. So we're going to eventually need to talk about what is the length of a little piece of curve like this and how do I go about computing or at least approximating the length of that piece of curve. I'm also going to need to know the value of the integrand. The integrand is evaluated as a function of location. Location means I'm going to need to know a point somewhere on this little piece of curve. So I'm going to say xi is just an arbitrary point on the piece of curve. and delta SI represents the length of that piece of curve. Okay. And so with all of that said, here's the way I want to define our new kind of integral, our chop it up, add it up strategy. We're going to take the size of each little piece of curve as I chop it up. Details, of course, to come, right? But the size, I'm going to multiply by the value of some appropriate integrand function at that location, xi. This product is intended to represent how much of, whatever my accumulating quantity is. Right? Am I adding up mass? Am I adding up mineral deposits? Am I adding up bacteria? Whatever it is, this product represents how much of that stuff is on each little piece. I then add up over all of the pieces, take a limit to make the round off arrows go away, and this is my new Riemann sum. Okay. All right, so this is a new kind of an integral. Here's the notation we're going to use for this kind of an integral. This is very common notation. The motivation for this notation, I think, is very easy. ds. Why do we use ds here? Well, it's to be as a reminder that what we're multiplying by is the length of each little piece of curve. The ds is just suggestive of the delta s. Yeah? Happy? Okay. Yeah. F. We put the f in here to indicate what is this function that is our integrand. What are we multiplying by size? Appropriate to the application. We're adding up. Okay, well, wait a second. Now we're adding. We've got all these pieces. We've got a bunch of different pieces. These are all pieces, though, of our domain. Our domain is the curve itself. Which is strange. It's a curve floating in space. It's not from some starting value A to some ending value B, and of course I mean the interval in between. No, we've got some curve, a complicated thing. That curve itself is the domain. So we indicate the curve as a subscript. That's where we put all of our other domains, so that seems like a reasonable thing to do. We use one integral symbol because, of course, this is a one-dimensional domain. We're adding up over a single direction. So I'm going to say I think this notation here is, dare I say, what else would we do, right? This seems like a perfectly natural choice. Okay, pause for any questions on that. We'll get to computing these in a few minutes. Okay. All right. So the first thing I want to do, though, is I want to talk about where do Riemann sums like this come up. Let's see a couple of actual examples of that. Again, keep in mind, it's very important not to just be able to compute things. If you can compute triple integrals all day long, you're really good at moving those symbols around, etc. You can compute all kinds of triple integrals. If you don't understand that a triple integral represents a Riemann sum and how to use Riemann sums to model actual applications, then what's it good for? Right? So we got to focus on first how do these Riemann sums connect to real world scenarios first, and then computing them will be sort of interest. All right. So a couple of examples. Let's see here. Yeah. Okay. So here's a question that I wrote when I was living. This is a long time ago, like 10 years ago. I was living in a house in Chapel Hill. Odd circumstances, but it had a very long driveway. The driveway was ridiculously long, and it occurred to me, man, I hope it never snows, and I have to shovel. That I would never be able to shovel that much. It was like, it was like 200 yards long. It was ridiculous, right? And so if I had to snow that, and my mind started to realize, oh my gosh, how much snow would that be anyway? And then I wrote this problem. Right. So the question is, we've got this driveway that cruises along the property line. Let's say, like this. And there's snow that's accumulated on that property. So the snow, of course, now I'm going to use blue because it's cold. the snow, and this is not to scale, of course, but maybe the snow is kind of deeper over on one side of the property and less deep over on the other side of the property. I mean, snow doesn't fall just, sort of as a uniform thing. Maybe there's some trees over here. The wind is doing a certain whatever. So if that's the case, and given how this road sort of curves around, we can't just say, oh, well, we're going to take the length of the road, and we're going to multiply by the width of the road, driveway, and then we're going to multiply by the depth of the snow, and that would give us volume of snow. It's just not that simple because the depth is different over here, and it's different over here. Okay. So again, chop it up, add it up. That's what we always do here. And in particular, I'm going to associate to this curve as we take this curve. Right, as that curve is going along, here's that curve going along, to some little appropriate piece of that curve here of length ds, I can talk about how much snow there is on that part of the road. And the amount of snow there is on that part of the road is a simple little product. ds gives me that distance. The width is constant at whatever that is. And then I just need to know, well, how deep is the snow at that point? So there's going to be some, sort of rectangular box of snow sitting up here on top of there. So I need to know the depth of the snow here. I'll see, what did I call that? I called that H. Right, so this box here is the amount of snow that's on that little piece of the curve. Associated to this little piece of curve of length ds, the amount of snow is H times W times ds. Everybody on board? Okay. So for the entire curve, for each little piece of size ds, I'm going to look at H times W times ds. I'm going to add that up over the entire curve. So the expression goes. And here it is. The total volume of snow is the sum of each little total amount of snow, which we just agreed was on each piece, W times H times ds. And now it's we have a pretty ready motivation to want to be able to compute these kinds of integrals, right? By the way, this is called line integrals. I'll talk about that in a moment. Want to be able to compute line integrals because I need to know how much snow I might have to be shoveling, and that's pretty hard work. And it's I'm naturally curious about this. Any questions about this example? All right. So here's another more sort of obvious example. I suppose I have here's our a rod of non-constant density. Delta. This time though, notice density is a function of three variables, x, y, and z. Right? Well, no surprise. Total mass is the sum of each little piece of mass. Each little piece of mass is density times length. And so another example, it's a little bit less fun, but this is another line integral that I have natural motivation now to want to be able to compute. If I can compute line integrals, I can compute masses. Okay. So yeah, a little bit of terminology I sort of skipped through here. These are called line integrals. I am going to also call them scalar line integrals because it turns out, and y'all have no way to see this coming at the moment, but we're gonna find pretty soon there is another kind of an integral that very naturally should be called a line integral. But that is fundamentally different than this in a weird way. So I'm not going to talk about that new kind of line integral yet. We'll wait until we get there. But in order to distinguish this one from the other one, this one having as it does a scalar differential. the next kind of line integral we're going to see is actually going to have a vector as its differential. It's strange. We'll get to that later. Anyway, this has scalar differential and a scalar integrand. So we're going to call this a scalar line integral. Okay. All right. Okay, so to compute them, big picture strategy, we have, we've already talked about here, we have here a domain, which is a curve winding through space, and that's awkward, right? You might even say we have here an undesirable domain, right? And I'm using language with the intention of suggesting, kind of calling back memories of another circumstance where we had undesirable domains. And we had a great idea for how to deal with undesirable domains. Now, our previous domains were undesirable because they were, bumpy and wiggly and had corners or what have you. Right here, this is undesirable for different reasons. This is undesirable because it's dimensionally awkward. It's a one-dimensional thing in a three-dimensional world, and it's just, I don't know what to do with that, right? So, why it's awkward, why it's undesirable, doesn't change the fact that it's undesirable, and I would like to change to a different domain. And our idea, way back when, yesterday, was that if you have an undesirable domain, find a way to view it as an image. If you can view that as an image of a more desirable domain, then we can talk about the strategy of pulling back, right? And the integral that we initially encountered defined on our undesirable domain, by pulling back through this function, we could get instead a new integral defined on this pullback domain. And as long as we're clever enough to make a pullback domain that's actually better, easier, more desirable, then this is going to be a win. Yeah. Okay. So this was change of variables a couple days ago, or yesterday, whenever that was. Okay. So, curve in space. Can I think of some way to view a curve in space as an image of something? And the answer is yeah. Well, in fact, we've done this a million times already. That's what a parametrization is, right? So lucky break, we already have the tool that we want. Right? Sometimes everything just comes together. So we just need to think about parameterizations, right? So here's an example of a parameterization. If you are looking at the upper half of the unit circle in R2, it is an image. The upper half of the unit circle in R2, now that's a dimensionally awkward as a domain, right? It's a one-dimensional thing. It's a curve, right? Part of a circle is a curve, but it's in a two-dimensional space, dimensionally awkward. But here it is as an image, aka here is a parameterization of it. Okay. All right. So we're going to take our parameterizations, and you'll notice now I'm using this notation to represent that function because that's the notation we use for parameterizations. And I'm going to proceed with the pullback strategy. Remember, the pullback strategy is think about how when you chop up your new domain, you are in effect chopping up your original undesirable domain. Let's think about how this piece relates to this piece. Let's see what I'm going to need to know. I'm going to need to know how big, what is the length of that little piece. And specifically, I would like to know how much, by what factor is this ds, by what factor is, the size of my new piece of domain over here, by what factor is that different from the size of this piece of domain over here? That's just our stretching factor circumstance, right? I find myself adding up a bunch of things multiplied by ds. ds is not the same as dt. but I want to rewrite it in terms of dt. And so I need to know ds equals what times dt. And again, said different, the way I like to think about this geometrically is how much does this little piece of curve get stretched when I come over here into the world. Okay. I'm going to approach this in a way that's really analogous to the way we approach this with change of variables. We drew a picture kind of like this in change of variables where we said, well, there's a vector that represents the displacement over there, that vector E1 dt. Now, when we were doing change of variables, we were looking at little pieces of area over here. We were looking at a little rectangular box, and we had E1 dt, and we had E2, or we had E1 du, I guess it was, and then E2 dv. We looked at both of those little vectors because those described my subrectangle. Here I don't have a subrectangle. Here I just have a little sub-interval. There is only one direction to go. The direction is E1. The size of this thing was dt, so the magnitude of this representative vector, it's just dt. So the vector is E1 dt. And I want to know what is the corresponding output vector over here. I'm going to call that dx. Okay, so the idea is, our linear approximation of where this vector goes is that vector. How do I relate these two vectors? Well, input change, output change. The relationship between input changes and output change. This is the derivative transformation. So notice this is the same argument that we were talking about with change of variables. With change of variables, with these input vectors, we found the corresponding output vectors by simply applying the derivative transformation. Here we go. By the way, a quick observation for notation. I'm calling this dx. You'll notice I'm using the x vector. The idea of the x vector represents position, x comma y comma z. dx simply says, what is our differential change in position? I was here. I'm now over here. dx represents my linear estimate of that change in position. So, natural notation. Okay, so, passed over here. Here it is. So, here's how we compute dx. dx is what you get when you apply the derivative transformation to E1 dt. That's what the derivative transformation does, right? Input vector, output vector. Hope that looks familiar from the change of variables argument. Here's another thing that might look familiar from the change of variables argument. This scalar factor of dt factors right out. What remains? Derivative transformation applied to an input vector. Standard basis vector. It's just a derivative, right? I'd say it's in the change of variables context, it was a partial derivative. Here there's only one variable. There's only one input variable, just t. And so it's just the derivative. Here, I'll circle the whole thing. It's just the derivative. X prime. Okay. Otherwise known as the velocity. Okay. Now, we do get to a nice punchline then, those that this dt carries along. So I wanted to phrase this argument here in terms of how the derivative transformation applies, because I wanted to extend the pattern. I wanted you all to see that the pattern is that the derivative transformation is what turns, input changes into output changes, and this is how we can, in general, in future contexts, which there will be some, using the derivative transformation to relate input changes to output changes, that's how you sort of get things done in this sort of problem. But that said, there is a much easier way to get this conclusion, and that is that is an old fact of physics that displacement is velocity times time. Right? So the result is exactly what we know we should have gotten. So let's call that a good sanity check. But again, repeating myself, but I do want you all to see the derivative transformation point of view on this. Is everybody happy with that? Any questions? Everybody good? Okay. All right. And so ds is the magnitude of dx. Let me go back to the picture. Here's our picture. You can see that the ds that we're looking for is the magnitude of that dx vector. Magnitude of dx. So the magnitude of v dt, and of course that gives you magnitude of velocity times dt. In other words, again, more familiar physics, distance equals speed times time. Right? That's ultra basic physics. Okay, so we've got our stretching factor. Input size, we have now successfully related to output size. Reminder, that's what we needed, right? That was our goal early on here. Passed it up. Here it is. Yeah, I was looking at a little piece of the domain of size dt. Needed to know what do I multiply to get this corresponding length ds. ds equals what times dt? And now we got it. That you might call the stretching factor in this context. The stretching factor is the speed of the parametric curve, the magnitude of the velocity vector, the magnitude of the derivative of the parameterization, however you want to say it. That's your stretching factor. So we're in business. We can do these. We can do integrals on these kinds of domains now, because we have successfully viewed this domain as being an image of that domain, and furthermore, we have also figured out what the corresponding stretching factor is, and so we can just a matter of writing it down at this point. We can write down what the corresponding pullback is, and we're going to rewrite an integral Riemann sum. How much snow does it take to shovel my driveway? How much mass is there in this bent rod? How much mineral deposits are there in this odd-shaped cavern? Right? All integrals defined, Riemann sums defined on this ugly domain. I can pull them back and turn them into integrals on the t-axis from A to B, right? The super easy single variable calculus domains. And here that is. As part of the pullback, the function is now a function of t. Right? Position is a function of t, and f is a function of position. So altogether, the function is a function of t. ds is speed times dt. There's our stretching factor that we just computed. So don't forget your stretching factor, otherwise plug and chug, and our scalar line integral is now written as a single variable calculus integral. Is everybody on board? Okay. All right. Okay, so I'm going to show you one example, and the other example you can read for yourself. It's just details, and this will be a good stopping point for today. But let's do this one example. So it's a bent rod example. Compute the mass. Not that what this application is really matters, right? If you want to do the snow example, go ahead, right? But what we're working on here is how to actually evaluate line integrals. So we were given here rod following a certain curve with density given by a certain formula, and we argued previously that mass accumulates and therefore is an line integral of density. We want to compute this out. Our curve is the top half of the unit circle in R2. Got to parameterize it. This is the parameterization of that top half of the unit circle. Reminder, just for analogy purposes, if you want to do change of variables, you got to find your change of variables function. Right? Your change of variables function is the thing that you use to pull back into your pullback domain. This parameterization is effectively, it's playing the role of our change of variables function. This is what we pull back through to get the pullback domain. So step one, of course, then, is to parameterize your curve. So there it is. And now let's see here. According to this formula up here, I'm going to need to know the velocity, because the velocity is the thing whose magnitude is my stretching factor. So alrighty, we're going to have to take that curve, compute the velocity. A little bit of calculus there, right? So the velocity is x prime. The derivative of this vector valued function, we take the derivatives one component at a time. Hope this is old news, right? We talked about derivatives of parametric curves back in chapter 3. One of our first things. And this magnitude happens to be 1. And everything else is just a matter of details at this point. So density is a function of position. Position is now a function of time. So density as a function of time is that. Reminder, what was position as a function of time? That was the parameterization itself. Position was cosine t comma sine t. Right, so notice, you can see right here, I'm just plugging in position is cosine t comma sine t. Okay. By the way, our density function was this, x squared plus 2y squared. That's our density function. Let's evaluate that. Here it is, x squared plus 2y squared. Well, there it is. This is x squared plus 2y squared, because x is cosine t and y is sine t. Okay, on the differential, ds, speed times dt. So in other words, it's just dt, because we worked out above that the speed was 1. That was this argument here. Everybody happy? Okay. And so notice we've got it down now to a single variable integral, and that's something that y'all can compute. By the way, last quick reminder, then we'll call it a day. Single variable integrals refuse to go away. They keep coming up. And this continues along in lots of areas of math, so this is not a peculiarity of multivariable calculus. So make sure that you can still do these kinds of integrals. If you're rusty on your single variable integral, if you've forgotten, for example, how to do trig integrals, there's a lot of different sort of versions of integrals involving trig functions in various different ways. Good time to brush up on those. You're going to encounter them. This is a nice example. So make sure you do this integral. Y'all have a nice day. See you later. And I'll see you in office hours if you're interested.